All right, let's get started here. Um, so we're doing unit 7. I don't think I had the learning notebook open until just recently, so you might have to refresh, but we're going to just go through this. So again, this is an odd number week, so we don't have a project or whatever, just the learning activity here. And the discussion thread, remember, you can either do a job posting if you haven't already, or anything from AI news. So anything related to AI, machine learning, things like related to self-driving cars or robotics or that sort of stuff will fall into this. We'll talk more about those later on in this class. We'll do a little bit about that. So for that. And again, we've got our explore activity where we have some different options about time series or recurrent neural networks that you can do for us. So we're just going to walk through the practice notebook today. So I'm going to go in here. I'm going to make a copy of it. And again, it has the write-up, so I'm going to go to the write-up, make a copy of that. This is an older notebook that I took from Jeff Heaton's work. He's in St. Louis long ago, and just sets up the basics. And I modified it quite a bit here, but I just want to reference Jeff and the original work he did on this. So standard stuff, we're going to import our libraries here. Then we're going to talk about these recurrent neural networks. I'm actually going to start some of the training, I think, and then I'll come back to this stuff, at least the first part of this a little bit. So I'm going to skip over this and this write-up part 1. I'm going to go on to this section 2, and I'm going to come back because there are going to be times where we're going to wait for this to do some training. And I have time to come back to this stuff. So we're going to look at recurrent neural networks. The first thing we're going to look at is networks that try to classify a set of words or a set of a sequence of things. This is often done with words to do like semantic analysis. Is this tweet positive or negative? Is it saying something good or bad, happy or not, or is it racist or not, biased or not? But we're not going to do that. We're just working with numbers. And so we're looking at this sequence of numbers. So I'm going to go down here where it says first try network and run this. And this is our inputs. And the idea is that we're going to look at a sequence of values. And you could imagine this as like looking out a window and seeing, is it clear outside the window or is there a car? This morning there was right outside my window, there was a plumbing or electrical truck there, and then it was gone. And later on, the neighbor was there. And so again, the idea is here is that we have these sequences of 6 inputs, 6 looks out the window or something like that. And so if it's a 0, we're not seeing anything. A 3 would be like a car, like maybe this is an electrical car or van showing up, and I look out again and it's still there. Now I observe and it's gone, and I observe and there's some other vehicle, something else there, and something else there. The other thing you can think of is just like holding up different things. If you look at me, I might be holding up nothing. I could hold up one thing, and I can put it down and not hold up something, and hold up something else and put it down there. And what I want to be able to do is something very simple. I want to be able to hold up objects, put them down, hold up other objects, and just ask you, what was the last object held up? And the last thing I held up was a blue marker. So you want to say it's a blue marker. here. So that's kind of what you're going to do. You're going to see stuff, it's going to go away. You're going to see something else, it's going to go away. And then we're going to ask, what was the last thing you saw for that? And each of these are a sequence of things. So like this one, maybe I show a 2 and I see another 2 and then it's gone. I see a 0 and then I see 2 again and 2 again and then a 0. Here I see a 3 and a 3 and then it's gone and it's gone and gone and gone. I have to just remember that the last thing I saw was a 3 there. So each line here is a set of observations. And for each line, I want to remember. So like this one, 1, 1, 0, 2, 2, 0. What was the last number, non-zero number I saw? And so the result of this one should be a 2 here. Here, because 2 was the last, again, hold up this little 1, it's gone. This is a 2, it's gone. And I say, what was the last thing you saw? You say, I saw a 2. For that. So that's how we're encoding it in here. So we have these, so this is our X, these are our inputs. I'm given a sequence here. So like maybe I'm given this sequence. And then these are our outputs here. I'm going to zoom in a little bit more on this. Okay, so these are our outputs. So if I see all zeros, the output's just going to be 0. If I go 0, 3, 3, 0, 1, 1, the last thing number I said was 1, the last non-zero number. So the output should be 1. This one, 0, 0, 0, 2, 2, 0, the output should be 2. This one down here, 3, 0, 0, 3, 3, 0, 0, 0, 0, 0, that should be a 3. So these are my outputs here. That match the last value in each of these inputs for this. So part of what you have to do up here is describe how do we interpret this sequence. So again, we're seeing a 0, we're seeing a 3, we're seeing a 3, we're seeing a 0, we're seeing a 1, we're seeing a 1. There. So, and then the next one is, if you see this sequence, should it be classified? Why should it be classified as category 2? And again, it's the last non-zero number you saw here. Now, the last thing we're going to do is that we're not trying to just predict 1 or 2. We're going to do a one-hot encoding of our outputs for this. So we are going to, rather than saying 2, we're going to do this output. Let me see if I can make this a little wider here. We're going to do a 2 output this way. So not a 0, not a 1, a 2 and a 0. So we're going to use one-hot encoding for our categories here, which we do a lot with neural networks, is one-hot encoding for the outputs. Because basically we're going to have 4 output neurons, and we just want one of them to be on and the other ones to be zeros here. So the first thing we're going to do is try to do this without a recurrent network. So I'm going to run this. I'm going to try to build just with dense layers. And this isn't going to work very well. I mean, it will work, it'll run. And my accuracy stays at about 3.4 the whole time. It actually jumps down to 3, jumps up to 4, but it's not very accurate. And here are my predictions. So this is what I expect. So I see all these sequences up here, and I try to predict what the right value is for each sequence here. So the first one's 0, and that's what I predict. The expected output is 0, and I predicted a 0. The next one's 1, and I predicted a 1. That's pretty easy. But the next one, I predicted a 3, but it was a 2. The next one, it should have been a 2, and I predicted a 0. And next one, it should have been a 3, and I predicted a 0. So the model's predictions were not very good compared to the actual expected values for this. Got a lot of things wrong. Because basically it's just guessing there. Sometimes it doesn't have any memory, so it might see the last value. So it generally gets these right where the last value is still there. It's kind of like if I hold up a marker and hold up another marker and I keep holding up that marker and I say, what was the last marker I held up? And it's still up in the air. You can say, oh, that's green. You don't have to remember anything. You can just look. And that's all this is doing, is that if it's still there, it will handle that. But it doesn't do it very well. So the second try here is we're going to try to run the code, the next code, set up the input basically the same way. And again, these are our outputs, one hot encoded outputs here. And we're going to build our network. And we're going to use this, rather than a dense layer, we use this simple RNN, simple recurrent network, neural network layer. And it starts and gets pretty accurate as it goes. I can kind of plot this, and I can have it predict. And it does pretty good. It wanted a 0 here, and it predicted a 1. This was a 1, and this was a 1. It got this right, got 2, this one right, this one it got wrong. It predicted 3, and it did a 1. So it doesn't match entirely. This predicted sequence outputs wasn't. So like if we look at this one, it got 0, 1, 2, 3, 4, 5, 6. The 6th one wrong. So I look at my inputs, 0, 1, 2, 3, 4, 5, 6. It got this one wrong. This is a kind of hard one. I see a 2, I see a 1, no 1, and then I don't see anything. I see 0, 0 for a while, and I have to remember what the 1 was the last one I saw. I hadn't seen it for a while. So that is a hard one to remember sometimes. So the first thing we want to do is just try it out and see, and it does okay. It gets to 57% accuracy. And again, I can see my predictions. More than half of the time it gets it right. But I can try, the next thing I want to do is try to train it longer. So the second try was just a simple recurrent network. Now we're going to try more training here. So find down here, we've got our simple recurrent network, but here we're training it for 50 epochs. Try to change this to 100 or even 200 epochs. I switch this to 200 and run this. It should train relatively fast, but the accuracy, so the accuracy went from, again, it was about 28%, up to 50%, back to 40, up to 64%, up to 78%, 78, 85%. It's learning more and more. 92, it gets up to 100% accuracy here. We get a nice curve where it gets right up to 100% here. And if we look at our results, it should get all the results correct at that time. So it learns, again, it takes a long time. It takes longer to train it, but it will learn this stuff over time. And again, you can also try some of these other, our next attempt, there's also some other layers. gated recurrent networks and short long-term memory networks, I can go into my network here. And here I do a simple RNN. I'm going to try a GRU instead. So I'm going to comment out the simple RNN by adding the pound sign. Remember, that's a comment. And I'm going to uncomment this GRU, the gated recurrent network here. So again, in this, these are my main network. I only want one of these layers active at a time. And so right now I have the middle one active. The other two, this one's commented out, it's in green. This one's commented out, it's in green. This one's not. Now I could train, if I train this for 200 epochs, it's going to get to 100% relative fast. I'm going to see if I can get to 100% in only 50 epochs and see if it'll learn pretty fast here. So it didn't, it only got up to 42. So maybe I'll try again 200 epochs and run this again. Again, this isn't a very hard problem, so all of these should be able to get up to 100% here if you train it long enough. So this will get there also, where I'm getting everything. My predicted outputs and my actual, my expected outputs, they should match exactly here. So again, so it learns. Basically, it's learning like if it sees a 2 and a 2 and a 1 and a 1 and a 0 and a 0. And then when it's done, I ask it, what was the last non-zero number you saw? It should remember, oh, I saw a 1 last, not a 2, but a 1 here. And if I show it like a 3, 3, 0, 0, 0, 0, and I ask it, what was the last number you saw, it'll say, I saw a 3 last. So it has a little bit of memory to it for this. So again, this is classification. We don't do classification that much. I mean, we sometimes do semantic analysis where we can ask, is this positive or negative? For a while, people were trying to earn money by looking at tweets and just trying to pick out companies that were in tweets and automatically determining if the tweet was positive or negative, and then having them buy stock before, really fast before other people bought stock. And people made a fair amount of money that way. There was a whole Trump bot where people were, we had computers following Trump's tweets back when Trump was president tweeting. And so anytime Trump tweeted about a company, there were computers that would try to figure out if it was a positive or negative tweet, and then either buy or sell that company based on that. Sell, maybe you can do what is called long and shorts. We won't go into, but you could kind of sell that even if you didn't own it. Okay. So that's the basics here of this. So again, this is our sequence where it's like either looking out the window or it's holding things up. What's the last thing you saw? 0, 3, 3, 0, 1, 1. And then we classify it this way. And again, if you do your simple RNNs here and you run this for 50, what percent were classified correctly? If you train it for 200, what percent were classified correctly? Questions on this? We're going to go on to the next part. And now the training is going to go slower here. So eventually I'll jump back to part 1. Trust me, I'll get back there. Okay. So rather than just kind of classifying this, we're going to try to do some forecasting here. And so we're going to generate some random data for us to forecast. So this stuff just generates some random curves for us to play with. Some random, and we're going to plot those out. So again, here's kind of our random curves. Now they're not entirely random. There's some random noise in them, but they tend to follow a pattern. They go up and then they go down and they go up and they go down. And there's some randomness in this pattern of up and downs. So we are using just some sine waves of different sine amounts to generate this stuff. So these are generating just these waves, but they're not exactly the same. They're a little harder to predict. So what we want to do is predict what the next value is here. So again, this shows the X as the next value. And you can kind of see it's going up, up. Each dot is a value, and then we're going up. So the next value should be up here. So that blue X is the right one. Now here, it's went down, down, and it was kind of level here. And it's thinking it should start going up again. Just kind of like here, it went up. And again, that's actually what the data does. This isn't prediction. This is just what the data is. So the X is the next value. So we're going to try to predict that next value. So we're going to show our network this sequence, except not show it the last value, and see if it can predict this last value in a couple different ways. So the first thing we're going to try to do is a naive forecasting test where we are going to, I'm just going to run this code, get this code, basically just predict what the last value is. And we're going to see how accurate it is. So like, if you want to predict the temperature today, a good guess is what was the temperature yesterday. So if it got to 20 degrees yesterday, it's likely to get to 20 degrees today, unless you live in Minnesota in March there. So if we're trying to predict our temperature tomorrow, maybe today's temperature is a good guess. Except tomorrow's supposed to get to 50 and today is not going to get to 50. But in most places, that's, again, stock prices. If the stock price was 110 yesterday, 110 today isn't a bad, it's better than 5,000 or negative 20 there. So if you're just going to guess anything, you're just going to guess what it was yesterday or the previous time. So that's what this is. So you can see these dots here. It is just taking the last dot and predicting the same thing. And again, it doesn't realize it's going up, but sometimes it's close here for that. So that's the naive stuff. And we're going to compare things to that. So we're going to look at our mean error score here. This is how off we are. So if this is an error, we want to get the error low. So by just doing this, we get the error down to 0.02. That's really good. So that's our goal. We've got to beat. If we say this is smart, it's got to be smarter than just saying same as yesterday. So we want to get a lower error than this. So here's our first attempt. We are just using the simplest network without any recurrent network. So we're going to run this and we're going to let this train here. And we're going to see what the output is. I'm going to train for 20 epochs here. Then we're going to graph things and print out our error. So right away, our error is getting smaller. So here, let me make notes of our errors so far. Okay, so our naive forecasting, our error was this. Gonna paste that in here. And then we did our flattened input. And that did better here. So we are down to this. And you can see this is going up, and it predicts it up a little bit. Here it predicts it up a little bit. Here it predicts it up. It's just always predicting it up in this case. Now, if I were to run this again with different random values here, I might get slightly different data here. So if I were to run this again, it might not be as good. So let's try this again. I don't remember if this generates new random plots or not. Maybe not. Now, one thing we find with these recurrent networks, I'm not running this on a GPU, but GPUs don't speed this up too much. And that's one of the issues with these recurrent networks, is that it's really hard to get these to go faster for training. So you tend to wait around, even though they're very small networks, you're just waiting for them a lot. So this is a network with a simple recurrent network of one value or one node here for this value. Let's see if we can get the results here. And again, here's my results. Mean squared error. This time it was 0.01. Last time, a lot of the, it was just predicting up a lot and learn that. So let's just talk about what this is doing. I'm going to scroll back up. Well, I'm going to go back here and try to get the next one, the deep RNN working, and get that training, because that's going to take a while. And then I'm going to go back up to 1 and talk about what is this actually doing. So recurrent networks have a connection that feeds back. It can feed back to the neuron itself, or a neuron on the same level, or a neuron on a previous level. It's not feed forward where it does send some information forward, it's activation forward, but it also has a recurrent connection that's either going back to itself or back to the previous node or layer for this. Now, how do we do this? When you're actually programming this stuff, if you're programming at the low level, what you have to do is you kind of have to remember not just its current state, but its last state. Because if there's a recurrent connection, then you have to look at the activation from the previous time, not the current update here. And so what you need kind of is you need a copy, an old copy of the neuron around. You need the neuron with its current activation that you're calculating, but you need its old activation also. And here we're calling this the context. So what we'll do is we'll copy its activation into a context and stuff. And I think this is a little better view of it here. We have some inputs. We feed it into our hidden layers. Here we have 2 hidden layers, and we have an output. So we'll do an update. We'll do an input. We'll activate these hidden layers, figure out what those activations are, and then we'll activate this output. But then we'll copy this hidden layer 1 node into the context layer node. And we'll copy this hidden layer 2 into this context 2. So we'll have a copy of it from the first update. And now we'll get a new update, new inputs, go in here. And then this, we'll look at the new updates, but also the copies from the last time. So it has a little memory of the last updates it did, and it'll update itself and then do the output. And then again, it copies itself, creates a context here, copies its activation. So every time these hidden nodes, they see not only the inputs, but what their values were last time. So sometimes we show this as context, sometimes we just show it as a recurrent connection back to itself here. Now, when we try to do learning gets hard because we have to back propagate through this, but they designed something called back propagation through time, where we're kind of unfolding this network and how this network can look. So here's at time t-1 and at time t. So this might be our second update. And then this is our first update, and then before that. And we can look at these connections through time. I'm not going to go over that because we really don't use back propagation in time, but we thought that was going to describe a lot of stuff. So for write-up 1, what are recurrent networks, how they're different? So recurrent networks are anytime we have some sort of recurrent connection back to a previous layer here. And then they should have some memory here. So they should remember past inputs or parts how they process past inputs for this. So again, if we're looking at words, it's very important that we remember the past words that came in to us here. Okay, let's see how I'm doing down here with my deep learning. Did I talk long enough? Okay, so let's see. So here's my deep learning network. I'm gonna grab that. So that's my next output. And this one I had 3 recurrent networks, one with 20 nodes, another with 20 nodes, and then one with an output, a single output node. And its mean squared error was down to 0.0028 here. I think I missed a layer here. We did the flatten. I forgot to copy and paste the simple recurrent network here. So the other one here was this simple recurrent network. So let's see, what would flatten? Let's see, this was the flatten one. So the flatten, okay, yes, flatten was actually this 0.0047. So flatten did pretty well, actually. Better than simple. A simple RNN, which is a little bit of memory, actually didn't do as well as the flattened one when I ran this. So that did this. So again, these are error values, and remember, we want as little error as possible. So this is you can think of the error value as the percent of time it kind of is off, or how much it's off. Some distance. So it predicted here and the actual value is here. So how much was that error? And there's little error here if it predicts very close to the values. Let's look at the graphs here. So you can see these graphs for this. This is going up, going down, up, 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 up to here, and it's predicting the red dot. And the blue X is the actual value. So it's doing pretty good at that prediction. Same here, going down, down, and then it's predicting it should go up now, and it does. Basically, it's that right on the nose. Here, it predicted the red dot and it was actually a little higher than that. And here, basically right on the nose for this. And here again, so it's with this deep network, it is forecasting pretty good for this value here. And you can see our errors getting much lower. It's 10 times better than this. So it was 0.002, 0.02, and now it's 0.002. So much smaller error. So this would say, like, if we know our temperature today, we can predict tomorrow's temperature. Or if you know the stock price today, we can try to predict the stock price tomorrow. But I really want to know what's the stock price going to be on Saturday, not tomorrow. There. So I want to predict not tomorrow, but the next day or the next day after that. So how do I predict ahead? And this technique is what got us to large language models here, where we can predict the next word, but if we can predict the next value, we can redo our network and say, okay, let's just pretend it was right. What's the next value after that? So here we're going to generate some sequences. We're going to set some stuff up, and we're going to plot and try to generate multiple things. So what it is doing, it is predicting the next value, and then we are adding that next value to our inputs and predicting the next value after that. So this is actually running predictions. It is calling predict 10 times. And each time it is shifting our inputs down. So here's the blue data is what it was given. And then it is predicting the next value here. And then we give it this value, all this data again. We actually skip one of the inputs because we're going to add one. And then we pretend this is the output, or it knows this, and it predicts one more. And then we skip the first two and get the rest of the inputs, and then give it the next two values that it's predicted and have it predict the third. So the actuals is in red, and the forecast here is in blue for this. So you can see it does a pretty good job of trying to forecast this. At least it gets the general trend, like, okay, because again, this is the general, we go up and we go down, we go up and we go down, we go up, and we should be going down now. It doesn't know all this little noise in here, but it's predicting down for now. So that is what this is doing, is this sort of time series prediction here for this stuff. So again, in this section, which of the above networks perform the best? And again, if you just keep track, you can just put this all in here and just highlight this. In mine, the deep RNNs perform the best, the lowest error values. And again, once we have that, we can use this to predict the next value. Now, one thing we get into problems with predicting the next value is compound errors going like this. And we get this a lot in robots too, or other things where we're building on things. The issue is that if we predict a value and it was off a little bit, but then we use that to predict the next value, and that's off a little bit. Now we predict again. We've got a couple values that are off, and we're predicting our next value is off. So I don't know if you've ever seen any of the videos or studies where you have someone like in a field and you say, just walk straight, and you blindfold them and have them try to walk straight there. and you see what happens. You'd think you could just walk straight. Have you ever done this? Have you just blindfolded, someone blindfolded you, just walk straight across? We often do this in not so much fields, but if you do this on, well, it works well on a soccer field. It works also well on a basketball court, as long as you have someone there that makes sure you don't hit the wall there. But what happens is that you start walking, you're blindfolded, and you think you're walking straight, but you are turning ever so slightly. And over time, that air builds and builds, and all of a sudden, you are not walking north, you are walking west there, because these little incremental airs, so you say, I'm going to walk straight here, you close your eyes, and you think you're walking straight, but you are ever so slightly off, and you end up, I mean, one step wasn't bad, but by 10 steps, if you're only off a degree, by 10 steps, you're off 10 degrees. And by 90 steps, you're off 90 degrees for that. And same here, these forecasts can go wrong over time here. So that's why it's really hard to predict the weather more than, 48 hours in advance sometimes. Okay, the last thing we're going to do is we used to talk a lot about these long short-term memories and try to explain how they worked. Not really using those much anymore, so we're not going to go too deep into those here. But if you're interested, they have some really neat memory stuff in them here. They have a forget gate, input gate, and so we can try those out. So we're going to train these and see. So this is our long short-term memory. But again, the training takes a long time with these, and we can't speed it up very much. And the reason why it's kind of hard to say, but because we need to compute it once before we can, one step before we can compute the next step, is kind of why this is all tied together. It's hard to parallelize this and do multiple trainings at the same time. So we just, even though this is a pretty small network here, it just has 20 nodes, goes to 20 nodes, goes to 10 nodes here. We're still very slow to get this to work. But the idea is that this should be better here. So again, you can see the forecast versus the actual for this. And again, you can do the same thing for these gated recurrent networks here and see what values they have for this. So I'm going to let that run. Actually, I think, well, yeah, we'll let that run a little longer. Yeah. Okay. There's a kind of real example of this. We can look at the sunspot data for this. So I don't know if you like to watch the Northern Lights around here. I like to do the Northern Lights. I don't see them that often because I live in town. But I really like to get good pictures of the Northern Lights or just sit there and watch them. And so what determines what's their chance of having Northern Lights? Well, we need some activation in the sun, and the sun is more active when we have these solar storms. And another way of calling those is just sunspots, these dark areas, churning areas of the sun. And so the sunspots activity will go up and down every so many years for that. So here's some data on the month and the year and how much what kind of sunspot data we have. And we have this data going back to 1749. They started tracking this data here. And so we can see how this looks. So this, we could just import this sunspot data and we can graph. So this kind of shows, now the years aren't right on this, but every dot here is a year, and every, so the number of sunspots ranges from about 0 to 250 as we go. And we're going to convert that and you do some prediction with that here. And then we're going to try to train a model, a long short-term memory model here to predict this sunspot data. So we're going to do, here's our training stuff. Let's see, I'm going to see if I can actually run this. Yeah, I think. Did this training get done? Yep. So I'm actually going to run this. Let me run this stuff here for the sunspots. Okay, there's my data. I'm going to organize the data. Here's my graph of the data. Going to kind of normalize it and set up my training data for this. Going to convert, do some work. One thing we find is that there's a fair amount of work to set this stuff up into sequences. So what we're going to do is we're going to take this data and we're going to break it up into chunks. So we're going to look at like 100 readings, 100 months in a row, and then have it predict the next value. And then we're going to look at another chunk of 100 months and have it predict another value. And somewhere else, we're going to take 100 months and have it predict another value. So we're always going to give it a sequence of readings and have it predict the next one. So we have to do a fair amount of work to kind of get our data set up to do that here. Now we're going to set up our network and train our network, and it's going to be kind of slow. And this is the output here. So you can see the orange is the actual data and the green are the predictions. So you can see that kind of, it looks like it kind of makes sense there as far as following this sequence of patterns of sunspots. Now, just so you know, we are at peak sunspot activity now this year. Actually, I think it may have been last year, but we're up here in the high zone here. So if you want to start looking for Northern Lights, you have that. Consider that. Does anyone have a Northern Lights app on their phone? Aurora? Yeah, I have Aurora too. So I like that. Oh. So we can try to generate predictions with our graph and see how it goes. We can generate a bunch of predictions. Now, often these, again, get off over time. So here's a prediction of this. And you can try different predictions to try to get this a little more accurate over time. So this is trying to show some input here and see it'll predict. So I think the orange is the actual and the dotted line is the prediction. And this one just isn't that great. But again, you can try change it. My experience is that gated recurrent networks, the GRUEL networks, work better sometimes than the long short-term memory networks for this. So, but again, this takes a while. It's still training. It's only on training 39 of 100. Yeah. So, next week, we're going to look at more at attention and language stuff. I'm going to try to get you the project open even this weekend, but tomorrow and Saturday, did anyone do high school robotics? Do you have any high school robotics people here? Yeah. Okay, right. So the deck doubleheader, there's a big high school robotics tournament at the deck Friday, and actually I'll be there tonight watching some scrimmages, but I'll be judging all day Friday and all day Saturday. It's fun to see the high school robots. There's a lot of people at the deck. It's a huge event. So a lot of excitement. So I'll be doing that. So it certainly won't be before Sunday before I get this, but hopefully by Sunday I can do it, because again, I've got to update our unit here. But the next thing we're going to be doing is starting to look at generating images and some of the attention models going forward for this. So I'm gonna let you, I think, wrap up here. So again, you know the routine, do your write-up, submit your notebook. Remember, do your Explorer activity if you haven't there, and do your discussion posts if you haven't already. So you can stay around to do those if you want to do those. If you're already done with those, that's fine. So I'm just gonna let this run and wrap up here.